We continue with analytic functions, having considered holomorphic functions in the last video. And in this video, we'll be looking at harmonic functions and Laplace equation, still under the complex numbers playlist. Okay, so we talk about harmonic functions and Laplace equation. First off, talking about harmonic function, a function u, which is u of x, y, and z, is called harmonic if it satisfies the grad squared u equals 0, where the Laplacian operator, this is the Laplacian operator now. Laplacian operator that, grad squared u equals partial squared u, partial x squared plus partial squared u, partial y squared plus partial squared u, partial z squared in two dimensions, which we have seen before now, arising from the Cauchy-Riemann equations. We have partial squared u, partial x squared plus partial squared u, partial y squared equals 0. Okay. So let's look at the Laplace equation, the Laplace equation now. The equation partial squared grad squared u equals 0 is called the Laplacian equation. It appears in heat conduction, in steady state, and it appears in electrostatics and fluid flow, and of course in gravitational potential theory. So you can see the wide application of that. So how do we physically interpret it? So the Laplace equation represents a system in equilibrium. So the key idea is that there are no sources or sinks. This means no heat is being generated or lost in a system. If you're talking about a heat conduction system, then no electric charge is present if you're looking at an electrostatic system, and then the system is perfectly balanced. That's the idea. So the interpretation is that the value at any point equals the average of nearby values. Okay, so to talk about interpretation in different fields, like we've said already, for heat transfer, the quantity U is the temperature, and the meaning is that there's no heat accumulation. So because we have a balanced system, the quantity of heat coming in is the quantity of heat going out. So there's balance. Then for electrostatics, we have electric potential. No charge is present. So as charge is coming, it's also going out. Then for fluid flow, we have the velocity potential for an incompressible flow, like that. So talking about properties of harmonic functions now, we have the mean value property. The value at a point equals the average over a surrounding region. So by way of illustration, right, I can say that, if you have, let's say this is a kind of fluid or something like that, or anything, maybe charge, heat, or anything. So if I take this point, this heat now, so the quantity of heat here is an average of the surrounding the heat around it. So if I pick this one now, so the value of this heat here is the average of the one surrounding it. If I pick this, so its value is the average of the ones around it. So that's the idea of that. So take this particular point. So it's an average of every other thing surrounding it. And that reminds me of about something that people say about the quality of a man's life. Like somebody's worth, like people say, is the average of maybe five people that surrounds the person, something like that. So, I mean, the value at a point equals the average over a surrounding region. Then we have the maximum principle. So the maximum and minimum occur on boundaries. So no interior peaks unless constant. So the interior is usually like an average of every other thing. So at the exterior, at the boundaries, you have maximum and minimum points. Then for uniqueness now, solution is uniquely determined by boundary conditions. So let's look at an example here. So check if u of x comma y is equal to x squared minus y squared is harmonic. So first of all, you want to compute the second derivative. First derivative, partial u partial x is uh is 2x. Differentiate again, you get 2. Same goes for minus y squared. Partial u partial y is minus 2y. Then partial squared u partial y squared is minus 2. So then if you add the two together, 2 minus 2, you get 0. Then this function right here is harmonic, like that. So if the second derivatives with respect to each of the dependent variables, add up to 0, then you say the function is harmonic. In example 2 now, if you want to check if u of x comma y equals x squared plus y squared, that is harmonic. So differentiate this twice, you get to. Differentiate this twice, you get to. So add them together, you get 4. So since it is not zero, the function is not harmonic. So the final result here must be 4 for you to say the functions are harmonic. And that is why in the previous video, we had a question to find the harmonic conjugate. So the harmonic conjugate is the function whose second derivative, uh, when added to the first one, you get zero, something that kind of thinking. So for solving Laplace equation, right? How do you solve Laplace equation? You can use separation of variables. Now, if you check my playlist under partial differential equations, under differential equations in general, I dealt with this a lot. They're solving differential equations. So using separation of variables, right? You can assume that u of x comma y is x, x, y, y. That is, you are splitting them up into the real part and the imaginary part. So if you then substitute into Laplace equation, you discover that you then have x prime prime over x plus y prime prime over y equals 0. And then you can say this is equal to minus lambda, while y prime prime over y is equal to lambda. And then you can have x prime prime plus lambda x is 0, y prime prime minus lambda y is 0. And these ones have standard solutions, which we are going to see in passing. Though I'm not going to be solving them in depth, but if you want solutions on boundary value problems and everything, check my playlist on either numerical analysis. Okay, I think I aggregated everything under differential equations. Just go and check for boundary value problems there. So solve Laplace equation in a rectangle that is x lying between 0 and a and y lying between 0 and b. So for boundary conditions, now you have u of 0 comma y is 0, u of a comma y is 0, u of x comma 0 is 0, and u of x comma b is f of x. So by the time you are done solving, in fact, I'm sure I solved this particular kind of problem in one of those videos, either under numerical analysis or differential equations for boundary value problem. So you have u of x comma y equals summation from n equals 1 to infinity of b sub n sine n pi x over a sine n pi y over a, where b sub n is 2 over a sine n pi b over a, integral from 0 to a of f of x sine n pi x over a dx, like that. That's the boundary value problem. But of course, we can write the Python code for the numerical solution. So here you have to create mesh. So you need to do some kind of discretization and all of that. So for the numerical solution to that problem now, so we have boundary conditions u of whatever here, 0, 0, then u of, so here now, we're talking about xy, right? So here, y is 0, and we take all values of x. Here, all values of x are minus 1. You have 100. Then all values of y and x is 0. We have 0. All values of y and x is minus 1. You have 0. Then we have an iterative solver, which we define for I in range 5000. So it's more like you keep doing that iteration, and we keep updating until we get the final result. And so when we do all of that, we end up we get this kind of Laplace equation solution. So it's more like you have heat flow or whatever might be flowing, be it charge or flow or fluid or anything like that. So where you have this yellow place, that's like the where you have the highest concentration. Like maybe if it is heat, now this is like the hottest part. So it's like you have it moving from the hottest part to the coldest part, where you have 0 down here. Okay, so explanation of numerical method now. So we have grid represents a plate. So boundary values are fixed. So interior values are updated using average. So as you can see that, then we have uij is 1 over 4 ui comma j equals 1 over 4 ui plus 1 j plus ui minus 1 comma j plus ui comma j plus 1 plus ui j minus 1. So this reflects the mean value property of harmonic functions. So if you, like I said, if you check my playlist on numerical analysis, there's a part where I talk about numerical solutions to partial differential equations or things like that. So you see all these discretization there. So the key takeaways from all we have done here is that harmonic functions satisfy phi squared u equals 0, and they represent equilibrium states. So values are smooth and stable, and boundary conditions determine the solution completely. So if I would also refer to how the derivation is done again, we start from the okay, I guess I need to change this now. I've used this a lot. From the Cauchy-Riemann equations, from the Cauchy Riemann equations, we have that partial u partial x should be equal to partial v partial y. That's one thing there. And then we also know that partial u, or better, yeah, partial u partial y now should be minus partial v partial x. So if we take this further and we differentiate the second time with respect to x in each case, if we differentiate this with respect to x, yeah, so we have partial squared u, partial x squared plus, equals, right, equals partial squared v, partial y, partial x, differentiate with respect to x, that one. Then if we differentiate this with respect to y, uh, so we take differentiate with respect to x. So on this other hand now, if we differentiate, we now differentiate this with respect to y. What do we get? So we have partial squared u, partial y squared equals minus partial squared v, partial x, partial y. So if we say this is equation 1 now, and this is equation 2, just this and this. If we then add 1 and 2, if we add equation 1 and 2, what do you get? You get here that partial squared u partial x squared, add this and this, so you get partial squared u partial x squared plus partial squared u partial y squared. And that is equal to, on this other hand, you have partial squared v partial y partial x. So partial squared v partial y partial x. And down here, you have minus partial squared v partial x partial y. By the way, partial squared v, partial squared v, partial y, partial x is the same thing as partial squared v, partial y, partial x, partial y, right? They are the same. So if you take any function and you differentiate, whatever you differentiate first, it doesn't matter, you get the same result. So that means these two are essentially the same thing, okay? So it means so we can say partial squared u, partial y squared, partial x squared, right? The first one is x squared plus partial squared v, okay, plus partial squared u, partial y squared is the same thing as 0 because these two are the same. So this is where we have that partial squared u is equal to 0. That's the Laplace thing we're talking about. So we can do the same thing for partial squared v. All right. All we just need to do is we differentiate this with respect to uh y, and we differentiate this with respect to x, and we tidy up again and we get the same results. So that's where the harmonic functions come from the Cauchy-Riemann equations. So we have some practice problems as usual, and I'm going to solve two of them like I've always done. So we uh, see questions 1 to 10 right here. And then you have questions 11 to 20. Okay, that's a bit lengthy. Okay, it can still fit. Yeah. So 11 to 20 like that. So I'll solve two of them as usual. Um, Let me see which ones I like to solve. All right, so I have to do two of those, right? The first one, so I have I'm taking to problem 10. So verify that u of x comma y equals arc tan y over x is harmonic. That is away from x, because if x is 0, that's going to break down, right? So we want to verify that it is harmonic. That means that if you differentiate it twice with respect to x and you differentiate it twice with respect to y and add together, you get 0. That's simply what that means, basically. Then the other question, so I'll be solving 10 and 20. So for 20, okay, that's a lot of work there, but I'll see to it. Using the final difference method, write the update formula for Laplace equation and explain its meaning. So you have u sub I comma j equals 1 over 4 into u plus 1 comma j plus u sub 1 minus I minus 1 comma j plus u sub I comma j plus 1 plus u sub I comma j minus 1, like that. So yeah, let's go ahead and do that. I'm taking questions 10 and 20. So problem 10 now, problem 10. So for problem 10, we want to verify, want to verify, to verify that u of x comma y is equal to arctan y over x. Actually, I prefer to write it like arctan y over x. That's the way I like to write it. So I'm going to do it that way. So we want to verify that that is harmonic. It is harmonic away, away, a harmonic away from x equals 0. Okay. So we then have so we go for step 1. Step 1, we do first derivatives. First derivatives. So what do we say here? We say let u be equal to arctan of y over x. So if that is the case, right, what do we then have? So using chain rule, using chain rule, we have u partial x. We're differentiating with respect to x now. That will be, this is the same thing as arctan of yx raised by minus 1. For this way, it's easy to differentiate. So using chain rule here, what do we have? We have when you differentiate tan, right? You get when you differentiate arctan, you get 1 over x squared. So in essence, you have 1 over 1 plus y over x all squared. In case you don't understand this, you can check my playlist on basic calculus. So that can help. When you differentiate arctan of x, y equals arctan of x, right? You're going to get tan y equals x. And by the time you're done, you're going to get 1 over 1 plus x squared. That's exactly what is happening here. So 1 over 1 plus y over x all squared. And then you have the derivative ddx of y over x. ddx of yx raised by minus 1. That's why I wrote this one like this. So you have partial u, partial x to now be 1 over 1 plus y over x all squared. So um when you differentiate yx raised by minus 1, right, you get minus yx raised by minus 2, like that. So that partial u partial x now, partial u partial x is now 1 over 1 plus y over x all squared times minus y over x squared. So we can tidy that up a little bit. So partial u partial x is equal to 1 over 1 plus y squared over x squared multiplied by minus y over x squared. So partial u partial x is equal to, so up there is 1. LCM here is x squared. So you have x squared plus y squared times minus y over x squared. So this simply means that partial u partial x is equal to, this x squared can go up. So you have x squared over x squared plus y squared times minus y over x squared. So this cancels out. So partial u partial x is simply, so you have partial u partial x to be simply minus y over x squared plus y squared, which is one of the things we need. On the other hand, we can then do the same for y. Okay, so again, we go for y. So also, since we have u to be arctan, arctan of y over x, which I like to write as arctan of, okay, let me bring it down now, which I like to write as arctan of yx raised to power minus 1. So in this case, it's easier because we are dealing with y. So again, we have partial u, partial y, which is 1 over 1 plus y over x all squared, multiplied by partial y of yx raised to power minus 1. So that's more straightforward. So you have partial u, partial y equals 1 over 1 over 1 plus y squared over x squared multiplied by, when you differentiate yx raised to power minus 1, y disappears. So you have x raised to power minus 1, right? So then you have partial u, partial y equals 1 over LCM down here is x squared. So you have x squared plus y squared multiplied by 1 over x, right? So that you have partial u, partial y equals x squared goes up all over x squared plus y squared times x times x. Oh, times 1 over x. I already put it down. So x cancels one of these, right? So partial u, partial x is equal to partial u, partial x is equal to x all over x squared plus y squared. So we have this again. So we want to prove that it's harmonic, right? So that means we need second derivative. So next, so step two, we get second derivatives. Second derivatives. So to get the second derivatives, what do we have? The first derivative, partial u, partial x, is simply minus y over x squared plus y squared. So to get the second derivative, um, I'm trying to look for a very easy way. Okay, yeah, we can do it. So partial squared u, partial x squared. We can use quotient rule. So let me make this minus y actually. So that's, if this is u and this is v, right? And we are differentiating with respect to x. So we have u quotient rule, right? That'll be v du dx minus u dv dx all over v squared. So usually, so that means that we have partial squared u, partial x squared to be equal to v in this case is x squared plus y squared. Du dx now is minus y, that differentiates with respect to x. That will just be 0. Okay, that makes life easy because that's just minus y. So everything there is 0. Differentiate y with respect to x, you get 0. Minus u. U is minus y, right? U is minus y. Then the v dx with respect to x, you just get 2x there. Thankfully, y is constant, so it goes. Then v squared, you have x squared plus y squared, all raised to power 2. So this goes easily. So you have partial squared u, partial x squared equals, so since this is already 0, minus and minus is plus. So you have 2xy up there, all over x squared plus y squared down here. So we have partial squared u, partial x squared settled. So we have another race with y. Y is x over x squared plus y squared, right? So, I mean, partial u, partial y. Partial u, partial y that we derived before is x. This is x over x squared plus y squared. So that's x over x squared plus y squared. Again, we do the same thing. This is u and this is v. So we know that partial squared u, we know that partial squared u, partial y squared will be v du dx. Oh, it's about y, right? Yeah, this will be about y. So v du dy minus u dv dy all over v squared. So all over v squared. So that's partial squared u, partial y squared equals, what is v? V is x squared plus y squared, x squared plus y squared. Du dy, du dy is 0 again because that is x minus u is x squared plus y squared, right? No, u is x, u is simply x. U is x, that's this u up here. Dv dy, we differentiate x squared plus y squared with respect to y, which is simply 2y, all over v squared again, that's x squared plus y squared, all over, raised to power 2. So, partial squared u, partial y squared is equal to, this is gone, right? So we have minus 2xy all over x squared plus y squared raised to power 2. So that's the second derivative. So in step 3 now, step 3, we find the Laplacian, which means we are looking for partial squared u, partial x squared, plus partial squared u, partial y squared. So, and from what we got already, so that means a partial squared u, partial x squared is 2xy. Okay, this is 2xy all over x squared plus y squared squared. Then partial squared u, partial y squared is minus 2xy. I didn't complete this. That's minus 2xy. So this is minus 2xy all over x squared plus y squared raised to power 2. So they are the same, so they can easily cross out. So it means that the Laplacian, this whole thing now, this whole thing put together is what we call the Laplacian, which is this squared u that is equal to 0. So if that is the case, so since grad squared u is equal to 0, the function is harmonic. The function is harmonic for x comma y not equal to 0, 0. So if it's 0, 0, then it won't be harmonic. But if it is 0, if it is not that, then it's harmonic. So that goes. So we move on to problem 20. Problem 20. So for problem 20 now, so for problem 20, we need to, so the finite difference approximation, the finite difference approximation of the Laplace equation, is ui comma j equals 1 over 4 into ui plus 1 comma j plus ui minus 1 comma j plus ui comma j plus 1 plus ui comma j minus 1. So that's what we have there. So the derivation, so we go for the derivation. So if we starting from the Laplace equation, in 2 dimensions, we have partial squared u, partial x squared plus partial squared u, partial y squared equals 0. That's the starting point. So using central difference approximations, approximations, so we have partial squared u, partial x squared to be approximately ui plus 1 comma j minus 2ui comma j plus ui minus 1 comma j all over h squared. That goes for that. Then partial squared u, partial y squared is approximately now the focus, this is on x, right? So I plus 1. So you're updating the x here, but here it's on y, so it shifts to j plus 1. So you have ui comma j plus 1, ui comma j plus 1 minus 2ui comma j plus ui comma j minus 1 all over h squared. So if you add the two now, so adding, that's partial squared u, partial x squared plus partial squared u, partial y squared. If you add the two now, then you have ui plus 1, ui plus 1, not ui plus 1, comma j that we're adding these two together. So we have ui plus 1 comma j minus 2 ui comma j plus ui minus 1 comma j all over h squared plus ui comma j plus 1 minus 2 ui comma j plus ui comma j minus 1 all over h squared. All of that equals 0. That's from the whole idea of, partial squared x, partial squared u partial x plus partial squared u partial y squared. All of that is equal to 0. So if you multiply through by h squared, right? If you multiply through, multiply by h squared. So you then have ui plus 1 comma j plus ui minus 1 comma j plus ui comma j plus 1 plus ui comma j minus 1 minus 4 ui comma j. So, this ui plus 1 comma j here, then ui minus 1 this one comma j plus ui comma j plus 1 plus ui comma j minus 1 minus this minus 2 here minus here. So all of that is equal to 0. So because we now need, so we can then solve for ui comma j. So to solve for ui comma j, then we have ui comma j is equal to, this one has 4 with it. So if you transfer it to the other side, and then we divide through by 4, so we have 1 over 4 into ui plus 1 comma j plus ui minus 1 comma j plus ui comma j plus 1 plus ui comma j minus 1. And that's what we have there. So the interpretation is that the formula means the value at any grid, at any grid point equals the average. It is equal to the average of its 4 neighbors. Then 2, this reflects the mean value property, of harmonic functions. The fact that every particular point is an approximation of the point, is an average value of the point around it. Then it models steady state equilibrium. Then apart from that, we can talk about the physical meaning. So as far as the physical meaning goes, we see that heat flows until temperature stabilizes. Heat flows until temperature stabilizes. No point has excess energy. No point has excess energy. No point has excess energy. Then lastly, every point balances, every point balances its surroundings. Every point balances its surroundings. Then we can talk about the numerical use. Numerical use. So first of all, it is used in iterative methods. It is used in iterative methods like Jacobi, and Gauss Seidel. Interestingly, I have all of this. I've done all this under my playlist on numerical analysis. You want to check it out in case you want to learn about numerical analysis. Very detailed playlist like that. So then it's of course repeated repeated updates lead to equilibrium solution. So as you keep repeating the updates, it leads to equilibrium solution. So that's how that is about there. So with that, we come to the end of solving the problem. So this is what we've done. Use the finite difference method, write the update formula for Laplace equation and explain its meaning. And that's all we've done there. So again, check the questions and try your hands on them and see how well you understand the gist. Okay, let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for that. And if you have not subscribed, why not go ahead and subscribe right away? Hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges like being the first to see some videos or being the only one to see some videos actually. You can also request for PDF copies of my notes with which I teach some of these topics. I might be able to share some of the notes with you. Then we can also hang out either physically if you're in the same geographical location at any point or online to discuss whatever interests you on my channel, be it mathematics, data science, or anything else. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.